Okay, so we now continue after establishing the theorems, the squeeze theorem and other theorems involving the absolute value of a convergent, of a sequence. So we now move to common limits. So please go through these limits. Common limits, we have that, I'll just state a few here. Limit as n goes to infinity of xn is equals to 0 if x is less than 1, and it's also equal to infinity if x is greater than 1. Okay, then we also have this one, the limit as n goes to infinity of 1 plus 1 over n to the power n. This is e. Okay, let's put up another one, limit n goes to infinity of n raised to the power 1 over n is 1. Okay, so there are a lot of common limits. These common limits can be used to find the limits of other sequences that look like the common limits, that are closer to the common limits. Look at this example. In this example, we're given that to determine whether so we need to determine the convergence of a sequence an 1 plus 1 over 2 n to the power n. So take note that in the previous slides, on the common limits, we're given this one, 1 plus 1 over n raised to the power n. So if you have the denominator, it's the same as that power, and you have 1 plus this other part, then the limit is exponential. Okay. So that means even here, it looks quite similar, but we just have to make sure that we have this raised to the power what? 2n. So if it's raised to the power, if it's raised to 2n, then we are able to find its convergence. Okay, so what we can do is just make that an to be equal to 1 plus 1 over 2n, then we can put 2n over 2. We have not changed anything because the 2 will cancel with the 2 down there. But we don't want the power to be 2n over 2, we just want the power to be 2n. So that means we can do this. 2n, we put the brackets, half. Okay, then we can find the limit. Limit as n goes to infinity of an. This will just be equal to the limit n goes to infinity of this function okay. So this is the same as limit n goes to, okay, I'll skip that. We can take the limit inside there, and the limit of 2, this 1 plus 1 over 2n to the power 2n, we know it's exponential. So the answer will be exponential to the power half. So that's the limit. So the limit is a finite number, therefore the sequence converges. It's the same as square root of e. Okay, so that is how we determine the convergence of unknown sequences using the common limits of sequences. Okay. Okay, we now move to increasing and decreasing sequences. So a sequence AN is increasing if AN is less than AN plus 1. That is the case where you have A1 less than, A2 less than, A3 less than, and it goes on. And AN is decreasing if AN is greater than AN plus 1. So that is the case where you have A1 being greater than A2 being greater than A3 being greater than, and it goes on. So any function, any sequence that is either increasing or decreasing is known as a monotonic sequence. Okay, so let's have some examples. Okay, so AN is equals to 1 over N. Number 1. AN is equals to 1 over N squared. So for the first case, okay, let's have the third one where AN is equals to 2N plus 2. So solution, for the first one, let's find A1. A1 will be 1, A2 will be half, A3 is 1 over 3. We can see this is in that form. So AN is decreasing. Then we move on to the second one. We have AN 1 over N squared. Let's find A1. We have 1. A2 we have 1 over 4. A3 we have 1 over 9. Again we have that case. And AN is decreasing. Okay, and the last one, where we have AN is equals to 1, 2, N plus 2. So here A1, 2 over 3. A2 will be 2 over 4. A3 is 2 over 5. So again here we have 2 over 3 being greater than 2 over 4, greater than 2 over 5. So AN is decreasing. Okay, so we can have different sequences. Actually, this one where you have an is equals to x squared n squared, you actually find that this is increasing. Okay, so that's where we're going to end with sequences. Please try the tutorial questions and go through and solve them. And our next lecture is on series. Thank you so much.